session on 1D finite element problems. In the morning we had seen that if we have a one dimensional rod, we can split it into one dimensional finite elements with uniform cross section. That means the variation is only along the length, the area of cross section would remain the same across the length of the element. In this case, let us say the area of cross section is A, and we said that, let us say the position of this starting point of the element is x1, position of the end point is x2, and let us say the deformation at this point is q1, the deformation here is q2. We had said that u, the deformation at any point inside this element will be equal to n times q. We also derived the fact that epsilon, which is the strain at any point in the element, will be equal to b times q, and the stress, that is sigma, that will be equal to E times bq, where E is the Young's modulus of the element. Okay. So if we take this formulation, then we will now try to derive the expression for the potential energy in this object. Okay. In this body, the potential energy expression pi, the total potential energy we know is equal to half of the volume integral of sigma transpose epsilon dV. dV will become A times dx. Okay, that is the integral along the length, minus integral of u transpose F, that is body forces, into A into dx. Okay, again I am replacing dV by A dx. Again this integral is along the length of the element. Okay, minus integral of u transpose T into dx. Okay, so again this integral will also become over the length of the element in this case, and minus the potential energy contribution because of the point forces, that will be sigma ui pi. Okay, so this will be the expression for the potential energy in this problem. Of this first term is what we call as the strain energy u, okay, or the strain energy. Now this potential energy in this object, the potential energy in this complete object will be the sum of the potential energy in the individual objects, in the individual elements. Okay, so if I take this element as element number 1, 2, 3 and so on, so n elements, then the total potential energy of this body will be the sum of the individual potential energies. Okay, so if I use that, I can say that the total potential energy will be half of sigma integral over the length of sigma transpose epsilon A dx, okay, minus sum over all the elements of integral of u transpose F A dx minus sum of all integral of u transpose T dx minus sigma ui multiplied by pi. Okay, and this summation is over all the elements, that means summation over all the elements. Okay, I am using capital, so I will use that.
Won't there be a late term in the
Again?
Won't there be a late term in the third
In the
integration over area?
okay, good you ask that. See, if we have this of the element, right now we assume that all the forces are one dimensional forces. Okay, so if I am talking one dimensional forces over the over this element acting on the surface, okay, that force has to be along this. So then really only we are talking of some shear kind of forces. Okay, so instead of that force, instead of being on a per unit area basis, I can treat that as a force on a per unit length basis. Okay, so in this case this T that I have used is force per unit length. This is a one dimensional case. Okay, if it is a three dimensional case, if I have a three dimensional surface patch like this, I can have a force acting on a per unit area basis. Okay, that is a force acting on the surface, but that is a three-dimensional force. But now I have a one-dimensional force acting along the length. Okay, so I can effectively take that to be force on a per unit length basis. So this tractive force is a force per unit length and not per unit area. Okay, that is why that length term is not visible. Okay, so if I take each of these terms separately, let's first take this first term, that is the strain energy U in the element. So this strain energy in the element is equal to the integral over the length, half of the integral over the length sigma transpose epsilon A dx. Okay, let's try and evaluate this integral. This will be equal to half of integral of, we know that sigma is equal to E B Q and epsilon is equal to BQ. Okay, so sigma transpose would be nothing but, now E is a constant, so E multiplied by Q transpose B transpose. Okay, epsilon is nothing but BQ, so BQ, okay, into A dx, and this integral is over the length. Okay, if I continue with this, this will become EA by 2 integral of Q transpose B transpose B Q dx. Okay, now Q transpose and Q, they are both constant matrices. Okay, if you remember, Q is equal to Q1 Q2. Okay, and Q1 and Q2 are constants. Similarly, B transpose we said was equal to 1 over LE, where LE is the length of the element, multiplied by minus 1 1. Okay, so B transpose is also a constant, it doesn't vary with x. Okay, so this integral over the length, all these four terms are constant terms. Okay, so this will be equal to EA by 2 multiplied by Q transpose B transpose B Q integral over the length dx. Okay, so this, now B transpose is this multiplied by, sorry, I think this is B. Okay, and B transpose would be 1 over LE multiplied by minus 1 1 transpose. Okay, so integral over the length of dx is nothing but the length of the element. Okay, so this will be equal to okay, yeah.
When we are evaluating the integral,
Yeah.
we can actually account for the shape of that figure. Instead of taking rectangular pieces, even if you take the profile and put it here.
Okay. See, when you are evaluating the integral, you can take into account the profile. Okay. But our objective right now is that we want to make an approximation so that we have simple elements by which we can account for everything. Okay, our objective is that if we can do the analysis of one small element like this, we will be able to repeat that over the complete element and then do that. Okay, if you want to,
then linear approximation for N1 and N2 won't be correct for the profile.
Yeah.
We have to take quadratic function.
either quadratic or higher order interpolation, okay, depending on the profile. The moment you start doing that, you cannot extrapolate the analysis of one element to the complete body. Okay, and then you have any arbitrary shape possible. Okay, you're right, we can incorporate that in the integral. That is only going to make things much more complex for me.
Other things get complex.
Yeah. Okay. So this is what we get. Now B transpose into B. If I multiply these two matrices, I'll get 1 over LE squared multiplied by 1 minus 1 minus 1 1. Okay, well B transpose is a column vector of size 2, B is a row vector of size 2. Okay, if I multiply the two, I'll get a 2 by 2 matrix. Okay, so if I put this back over here, this is equal to half of Q transpose into EA multiplied by 1 minus 1 minus 1 1 okay. Is that okay? So this I'll say is half of Q transpose KE multiplied by Q. This matrix is what we'll call as the KE matrix, or we'll call this the element stiffness matrix. Okay, this element stiffness matrix is what we are getting over here, which is EA by LE multiplied by 1 minus 1 minus 1 1. Okay, and why do we call this stiffness matrix? That you can see from this expression. This expression for potential energy, this you can compare, let's say, with the potential energy of a spring, which is half k x squared. Okay, so this x is same as the deformation over here, and this k is a stiffness. Okay, so this KE is called the element stiffness matrix. It basically relates the deformations with the strain energy in the object. Okay, in fact, we will see when we go on for higher order elements and more complicated elements, our aim will always be to get this expression. We will always get U, that is UE, the element strain energy, to be equal to this expression, and we will try to get some expression for this stiffness matrix. This will be the first step in our attempt to solve the finite element problem. Okay, so this is what we call the element stiffness matrix. Now if we take up the potential energy terms, the second term over here, okay, that is the potential energy contribution because of the body forces. If we take this, then the integrals for this would look something like this. Integral over the length U transpose F A dx. Okay, we know U is equal to N times Q. Okay, and we know this F is a body force. So this integral, what will that become? U transpose will be Q transpose times N transpose. Okay, so if I replace that over here, I get Q transpose N transpose multiplied by F A dx. Okay, now F is the body force acting in the element. We said initially, if you take an element like this, over the length of this element we will assume the body force to be constant. Okay, if you have a number of elements connected together and so on, the body force in this will be different from that, and this will be different from that and this, but over the length the body force is going to be constant, okay, because we are taking elements to be small enough. Okay, so in that case F will be a constant, and A, again area of cross section, that is also constant. Q transpose into N transpose. Q transpose will be equal to Q1 Q2. Okay, N is equal to the matrix N1 N2. So N transpose is this. Okay, so this will become if I say Q transpose into the integral of N transpose dx multiplied by F into A. Okay, F and A are also constants. Okay, N transpose is this, so this will become equal to Q transpose F A into, now this N transpose is this matrix, so I will put that as integral of N1 dx integral of N2 dx. Okay, both these integrals are over the length. Okay. Now, what is the integral of N1 dx? If you remember the shape function that I had drawn, we said that this is my point 1, this is the point 2. Okay, N1 is equal to 1 at this point and is equal to 0 here, and it varies in a straight line. Okay, at this point this is the shape function for N1. N1 is 1 here and is equal to 0 here.
So if
Yeah.
integrating, then isn't this against the very concept of finite element methods? Because finite element, we mean that it has to be something infinitely small. When we take an integration over continuous
No,
period,
no.
we are not really defining what the
Finite element
is.
method
It's not finite.
doesn't say
Okay,
element has to be finitely
just
small.
I didn't get your question at all.
So,
You-
like when we say finite element,
Yeah.
we divide the structure into small finite elements and
Okay.
then do the analysis of this.
Yeah.
If we are integrating over the length, when we are not really defining any finite point, it's a continuum. Like this, the finite.
Yeah, see, what we'll do is we'll take this individual element. Within this element, whatever variation that we assume or whatever variation that we get, we will find out our equations corresponding to that. Okay, but variation over elements, that will not take care of. Okay, so over the elements we'll get some analysis for this, some analysis for the next one, and then we'll just sum it up. Okay, our aim is that we will take the elements small enough such that whatever assumptions we have made about this element, those assumptions will be valid. We have made the assumption that our displacements are moving, are changing linearly. Now that assumption will be valid only if my elements are small enough. If I take very large elements, that is probably not going to be true.
Yeah, values will be continuous at the interface of the two elements.
Okay, for instance, if I take a large element, my strain distribution might actually be like this. It might be any kind of curve. Okay, but within a small gap, I'll assume it to be linear. Okay, that is what the finite element method will tell us. Okay, but within this element, we have to do the integration according to our assumptions. Okay, so this N1, this is varying along the length of the element in this manner. Okay, and what is the integral of N1 dx? Integral of N1 dx is nothing but the area of this curve, the area under this curve. Okay, so integral of N1 dx is nothing but it will be the length of the element divided by 2. Okay, because this is a triangular area, we are taking linear shape function, so N1 is a straight line. Okay, so integral of N1 over the length of the element is going to be the area of this triangle, and that is nothing but the length multiplied by 1 multiplied by half, which is LE by 2. Okay, so use that expression over here, and this will become equal to half of Q transpose F A LE LE. Okay. So this is going to be equal to half of Q transpose F A L E multiplied by 1 1. Okay. Now this will put that as Q transpose multiplied by a vector Fe or matrix Fe, the Fe is equal to F A L E half half. Okay. Now what is Fa multiplied by Le? F is the body force acting on the element, A is the area of cross section, Le is the length. So A times Le is the volume of the element. What is F times ALE? That is the total body force acting on that element. Okay, so if I have an element like this that has some body force acting in this direction given by F, its area of cross section is A and length is Le. Okay, so the volume of this element is A multiplied by Le. The total force will be F into A into Le. Okay, and this Fe I am multiplying by Q transpose. Q transpose is nothing but Q1 Q2. Okay, so when I am multiplying Q1 Q2 by this, essentially what I am doing is whatever the total body force acting on that multiplied by half multiplied by Q1. Okay, Q1 is the deformation of this point. Okay, Q2 is the deformation of this point. Okay, the total force acting on this is, let's say, F. Okay, that is this term. Okay, so the deformation here is Q1, deformation here is Q2. I am saying that this potential energy is equal to F into Q1 by 2 plus F into Q2 by 2. Okay, that is what this multiplied by this will give us. Okay, so F into Q1 by 2 is nothing but, if I split this force F into two parts, one part acting over here and another part acting over here. Okay, then this force is F by 2 and this force is also F by 2. Okay, because of this force the contribution to the potential energy will be F by 2 multiplied by Q1, and because of this force the contribution will be F by 2 multiplied by Q2. Okay, so effectively what I am saying here is that the contribution to the potential energy can be computed by taking the total body force, that is F, splitting it into two parts, one part acting on the first node, one part acting on the second node. Okay, so this vector Fe or this matrix Fe is only telling me that half the force is acting on the node 1, the other half of the force is acting on the node 2. Okay, so effectively I am splitting this force into two parts, two equal parts, one acting on the first node, the other acting on the second node, and I say that the total potential energy contribution because of the body force is given by this expression. Okay, and this matrix Fe is what we call as the element body force vector. Okay. Now similarly, we'll evaluate the next term in our potential energy expression, that is this term. Okay. And for this term what we get is a similar relation, integral of u transpose t dx over the length. This is equal to integral of q transpose n transpose multiplied by t dx. Okay, because I know u is equal to nq, so u transpose is q transpose n transpose. We just did that. Okay, this is equal to t into q transpose into integral of n transpose into dx. This will be equal to t into q transpose into, again, integral of n transpose dx will give us the same thing, that is le by 2 and le by 2. Okay, this is the same as what we have just derived here. Okay, integral of n transpose dx is what we get here. Okay, the same expression I am using there. Okay, so this, let's say I'll say this is equal to q transpose into te, where te is nothing but t into le by 2 and t into le by 2. Again, T is a attractive force acting on a per unit length basis. Okay, so T into LE is the total attractive force on the body, on the element. T LE by 2 will be half of that, T LE by 2 is another half of that. Okay, so effectively what we are saying is that this attractive force can also be treated to be acting as if it is split equally between the two nodes, and we have half the force acting here and the other half of the force acting here. Okay, and this vector we can call it, let's say, the element attractive force vector. Okay, any questions up to this point? This derivation is very similar to the derivation we just did. Okay. Now the last term that we have in the potential energy expression, that is this term, sigma ui pi. In this, if we have a set of elements and so on, we can assume that all our point forces will be acting on some of the nodes. Okay, so our point force is acting only on the nodes. Okay, so if we have some element, then we can have some force acting here and we can have some force acting over here. Okay, so the contribution of the last term, sigma ui pi, I can again rewrite this as q transpose multiplied by, let's say, p. Okay, the p is a, let's say this force is p1, this force is p2. P is a vector p1 p2. Okay, transpose, and q transpose will be q1 q2. Okay, the product of these two will give me this term. Okay, because u at this point is nothing but q1 and u at this point is nothing but q2. Okay, because this u is the deformation. Okay, so the potential energy contribution because of point loads in this element, I can write it like this. Okay, so now if I look at the complete equation that I have, a potential energy pi the first term is a strain energy term, and I said that that term is equal to half of Q transpose K Q, KEQ. Okay. The second term, that is this term, is minus Q transpose into Fe. Okay. This term is minus Q transpose into TE, and this term is minus Q transpose into P, let's say PE. Okay. Now this, I'll again put that as half of Q transpose KE Q minus Q transpose into FE plus TE plus PE. Okay, and this is equal to half of Q transpose KE Q minus Q transpose into F. Okay, where this FE, capital FE that I have used, is what I call as the element force vector. Okay. Now this element force vector is found out by taking the body forces, the total body forces acting on the element, dividing it equally into two parts, one part at the first node, the second part at the second node. Okay. Taking the total tractive forces, dividing it into two parts, one part at the first node, the other part at the second node, and taking all the point loads both for the first node and for the second node, summing up all the forces on the first node, summing up all the forces on the second node, and making a vector out of that, or a matrix out of that. Okay, this is how we get the element force vector. Okay, so our potential energy of the element is given by pi, which is equal to half potential energy. This is energy of the element, Q transpose KE multiplied by Q minus Q transpose FE. Okay, and the total potential energy in the system pi, that will be equal to sigma half Q transpose KE Q minus sigma Q transpose FE. Okay. Any questions up to this? Okay. Then the next thing is that these expressions are for the potential energy in one single element. Okay. Similarly, this is also for the potential energy contribution in one single element. When I do a summation over all the elements, I can simplify these equations further. Okay, you can get them into one single matrix and then remove the summation. Okay, before going into that, let's take a simple example and see how we can get the KE in the FE matrices. Okay, so if we take a simple example, okay, let's say this width is 6 inches, at the center point is a force acting P equal to 100 units. This length, let's say if I take that to be 12 inches, Okay, the remaining length, let's say another 12 inches. Okay, let's say this part I take it to be 3 inches. Okay, if I take an object like this, I can approximate it by two elements which look something like this. Okay, the length of the first element is 12 inches, second element is also 12 inches. Okay, essentially what I have done is, at the place where this point force is acting, I split it like this. I have taken one element here and the second element somewhere here. Okay, and let's say for this element my area of cross section A, this is 3, this is 6, 9. I have taken a linear variation. So at the center, how much will I get? 4.5. Okay, this would be 4.5. So for this element I will get between 4.5 and 6. If I take an average, I will get the area of cross section to be 5.25. Okay, again,
Area of cross section will be this into 12.
area of cross section is in a perpendicular direction.
Yes, suppose depth is 1. So
Okay, if I take a unit depth, I get that to be 6 plus 4.5 by half. Similarly, the area of cross section here will 4.5 plus 3, that is 7.5. I'll get it to be 3.75. Okay, inches squared. Okay. Now, let's say this is my element number 1. This is my element number 2. Let's say I call this my node number 1. I call this my node number 2. And I call this my node number 3. Okay, so my element 1 is between node numbers 1 and 2. Okay. And element number 2 is between node numbers 2 and 3. Okay. Now, if I take the first element, for my first element, if I want to write down the KE term, how much is KE? What is the expression for KE? It is A1 E1 by the length of the element multiplied by 1 minus 1 minus 1 1. Okay, so this will be equal to area of the first element okay, this will be equal to area of the first element is 5.25. let's say the value of E, we take it to be 3 into 10 to the power 7 psi. Okay, divided by the length of the element, which is 12 inches, multiplied by the matrix 1 minus 1 minus 1 1. Okay, this is for element number 1. Similarly, KE for element number 2 is equal to, I will get A2 E2 by L2 multiplied by 1 minus 1 minus 1 1, and this will be equal to 3.75 into 3 into 10 to the power 7 divided by 12 into 1 minus 1 minus 1 1. Okay, so these will be the two element stiffness matrices. Okay. Now, if on this object I assume that there is a vertical force due to gravity, okay, I'll get a force which is per unit volume F to be equal to rho times g, where rho is the specific gravity. Okay. The total force acting on this element, that would be total force acting on the first element F1, that will be equal to its volume 5.25 into 12 rho g. The total force acting on the second will be 3.75 into 12 rho g. Okay. So if I take up my first element, okay, for the first element Fe will be equal to F by 2 acting at both the nodes. So that will come out to be 5.25 by 2, 5.25 by 2 multiplied by 12 rho g. No.
That will be Fe2.
See, I am looking at this element, and whatever the total force acting, half of it will act here, the other half of it for this node will act here. Okay. Similarly, if I take up the other element, I will get the body force will be 3.75 by 2, 3.75 by 2 multiplied by 12 rho g. Okay, and if I take the point loads, I have a point load of 100 units given at the node number 2, at this node. Okay, we will incorporate that later on when we talk about the global equations. Okay, we will just see how that can be incorporated. Okay, so as far as the elemental equations are concerned, we will get body forces given by this expression, element stiffness matrix given by this and by this and this. Okay, if I have this as the element stiffness, then the potential energy we have just said is half Q transpose Ke Q minus Q transpose Fe. Okay, so this Ke is this expression for the first element. For the second element, it is this expression. Okay, you are saying something?
Yeah. What about the force that is acting due to weight of the lower element on the upper element?
Okay. See, right now, what we have not done, we have said that the deformation here is, let's say, Q2, and deformation here is Q1. Okay, we haven't yet found out the expressions for Q1 and Q2. When we do that, even that weight will be taken into account. Okay, when we solve the global equations, your question will get answered. Okay, we haven't yet come to the global equations. Right now, I'm only telling you how to find out the different matrices. Okay, in the next class, we'll be talking of how to get the global equation and how to solve the equations. Okay, once I answer that, your question will automatically get answered. Any other questions? Okay, so I'll stop here now. In the next class, we'll talk of how to assemble the global equations and how to solve these equations. Okay.